Hello there and welcome back to the Science Sleepy Minds, that cozy little corner of the universe where we turn the incomprehensible into something soft enough to rest your head upon. Tonight, you find yourself standing on an invisible platform somewhere in deep space, and the view is absolutely absurd. Stars pepper the blackness in every direction, not as the sparse scattering you might see from your backyard on a clear night, but as a dense, glittering fog that seems to breathe with ancient light. You turn slowly, and the Milky Way sprawls beneath your feet like a luminous river frozen mid-flow, its spiral arms curling outward in lazy, elegant arcs. It is beautiful. It is enormous. It contains somewhere between 200 billion and 400 billion stars, each one a furnace of nuclear fire, many of them orbited by worlds we will never name. And here is the thing that should make your knees wobble just a little. Compared to what we're about to discuss tonight, our entire galaxy is a small-town diner sitting in the shadow of a skyscraper so tall its upper floors vanish into clouds made of galaxies themselves. You probably will not survive the sheer scale of what is coming, at least not with your previous sense of cosmic proportion intact. By the time we finish, the Milky Way will feel quaint, almost cozy, like a childhood bedroom you once thought was the whole world. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, drop a comment letting me know where you're watching from and what time it is there. I always love imagining this strange, scattered audience of night owls and early risers, insomniacs in Tokyo and stargazers in Sao Paulo, all drifting towards sleep while contemplating the same impossible distances. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You take a breath, though of course there is no air out here. So let us pretend your imaginary spacesuit is very accommodating, and you begin to drift upward, away from the Milky Way's galactic plane. The spiral structure becomes clearer as you rise, those grand arms wrapping around a bright central bulge like ribbons around a gift. Astronomers estimate our galaxy spans about 100,000 light-years from edge to edge, give or take some fuzzy boundaries where the stars thin out into the intergalactic void. 100,000 light-years. That means a beam of light, travelling at roughly 300,000 kilometers per second, the fastest anything can move in this universe, would need 100 millennia just to cross from one side of our home galaxy to the other. If you had started walking at the moment Homo sapiens first appeared in Africa, you would not have made it across the Milky Way's diameter by now. You would not even be close. And yet, as you continue to rise, the Milky Way begins to shrink beneath you. It becomes a glowing disk, then a bright smear, then a single point of light among many. You're now looking at the local group, the small galactic neighbourhood we share with Andromeda, Triangulum, and a few dozen dwarf galaxies that orbit us like nervous moons. The local group stretches across roughly 10 million light-years, a respectable chunk of real estate by any earthly standard, but still a mere speck in the grand scheme. Beyond it, galaxy clusters stack upon clusters, filaments of matter thread through voids so empty they make the space between stars look positively crowded, and the observable universe unfolds in every direction for about 93 billion light-years. Somewhere out there, roughly 1 billion light-years from where you once stood on that little blue planet, there is a galaxy so large that astronomers had to double-check their math when they first measured it. It is called IC 1101, and it sits at the centre of a galaxy cluster known as Abel 2029, like a bloated emperor on a throne made of gravity. Historians of astronomy still argue whether early 20th century observers glimpsed its true nature, or simply catalogued it as another faint smudge among thousands. But what matters is that eventually, someone pointed a sufficiently powerful telescope in its direction and realised they were looking at the largest known structure of its kind in the entire observable universe. You squint toward the constellation Virgo, which is roughly where IC 1101 lurks from Earth's perspective. though of course you cannot actually see it with your imaginary eyes at this distance. What you can do is begin to imagine it, and that is where things get deliciously strange. Our Milky Way, that proud spiral of hundreds of billions of stars, could fit inside IC1101 dozens of times over. Some estimates suggest you could line up 50 Milky Ways across IC1101's diameter and still have room for cosmic leftovers. Others are more conservative, but even the tamest numbers are staggering. We're talking about a galaxy that may span 4 million light-years, possibly 6 million, depending on where you draw the boundary between the galaxy itself and the diffuse halo of stars and dark matter that surrounds it. Let that sink in for a moment. 6 million light-years. A beam of light leaving one edge of IC1101 today would not reach the opposite edge until the sun has exhausted its hydrogen fuel and swollen into a red giant, until Earth has either been swallowed or roasted into a cinder, until whatever descendants of humanity might still exist have long since moved on to other stars, and that beam of light would still be inside the same galaxy the whole time. You feel a kind of vertigo that has nothing to do with falling, because there is no down out here, only an endless sense of expansion that presses against the walls of your comprehension. The Milky Way suddenly seems less like a grand empire and more like a single apartment building in a city that stretches beyond the horizon. And IC1101 is not just another building in that city. It is the building, the one that casts a shadow over everything else, the one whose foundations go so deep they tap into something fundamental about how the universe assembles itself. A quirky tidbit to tuck under your pillow: IC1101 is so far away that the light reaching our telescopes today left the galaxy over 1 billion years ago, back when the most complex life on Earth was probably still single-celled and utterly unaware that it would one day evolve into creatures who would build machines to peer across the cosmos. When you look at IC1101, you are not seeing it as it is now. You're seeing a billion-year-old postcard, a frozen moment from an era when the galaxy might have been even larger or slightly smaller, when mergers might have been in progress, when the whole structure was shifting in ways we can only infer. And here is a question that astronomers still debate in conference rooms and late-night email threads. How do you even measure something like this? Where does a galaxy end and the intergalactic medium begin? Is it where the stars stop? Where the dark matter halo fades? Where the gravitational influence gives way to the pull of neighbouring structures? The answer matters enormously, because IC1101's claim to the throne depends on which measuring stick you use, but we will get to that. For now, just rest in the knowledge that you're about to spend the next little while exploring a cosmic object so vast it makes our home galaxy look like a pebble beside a mountain. Breathe slowly. Let your shoulders drop. The universe is under no obligation to fit inside your head, and that is perfectly fine. Sometimes the best thing you can do is simply float alongside the incomprehensible and let it wash over you like a warm tide. You drift a little further from the Milky Way, watching it shrink into a pale swirl the size of a thumbprint, and you start to wonder what it actually means to call something the biggest galaxy. The phrase sounds simple enough. Biggest implies a measurement, a number, a clear winner standing on a podium with a gold medal around its metaphorical neck. But the universe, as you're learning, does not care much for human tidy categories. It sprawls and blurs and refuses to draw neat lines around itself, and so the question of galactic size turns out to be surprisingly slippery. You could measure a galaxy by its stellar mass, the total amount of stuff locked up in stars. This seems intuitive. More stars, bigger galaxy, right? But stars are only part of the picture. Galaxies are also filled with gas, dust, and vast quantities of dark matter. That mysterious substance that interacts with gravity but refuses to glow, absorb, or scatter light in any way we can detect. If you counted only stars, you would be ignoring the gravitational scaffolding that holds the whole structure together. It would be like measuring the size of an iceberg by looking only at the tip poking above the water. You could also measure diameter, the distance from one edge of the galaxy to the other. This is the number that tends to capture public imagination because it translates into something almost graspable, a length, a span, a sense of how long it would take to cross. But edges are tricky. Stars do not simply stop at a hard boundary. They thin out gradually, like the fringe of a forest fading into meadow. Some astronomers define the edge as the point where stellar density drops below a certain threshold. Others extend the boundary to include the faint halo of old stars that surrounds many galaxies like a ghostly envelope. Still others factor in the dark matter halo, which can extend far beyond the visible stars. Depending on your definition, the same galaxy can be 2 or 3 times larger under one ruler than another. Then there is luminosity, the total amount of light a galaxy emits. A galaxy blazing with young hot stars will outshine a galaxy of the same mass filled with older, cooler suns. Luminosity tells you something about a galaxy's star formation history and its current energy output, but it does not map directly onto size in any spatial sense. A compact galaxy undergoing a starburst could outshine a far larger but more quiescent neighbour. And let us not forget volume, the 3-dimensional space a galaxy occupies. Spiral galaxies like the Milky Way are relatively flat, their stars concentrated in a thin disk with a central bulge. Elliptical galaxies, by contrast, are more like 3-dimensional ellipsoids, puffballs of stars extending equally in all directions. If you compared a spiral and an elliptical with the same diameter, the elliptical would contain far more volume, like comparing a pancake to a grapefruit. IC1101 is an elliptical galaxy, and a particularly bloated one at that. Its stars are not organised into elegant spiral arms, but instead swarm in a vast, roughly spherical cloud, densest at the centre and thinning toward the edges. This shape is part of what makes IC1101 so enormous. It is not just wide, it is deep. A galactic 3-dimensional object whose volume dwarfs anything a spiral could achieve at the same diameter. Historically, astronomers began classifying galaxies in the early 20th century, most famously through Edwin Hubble's tuning fork diagram, which sorted galaxies into spirals, ellipticals, and irregulars. Hubble himself noted that ellipticals range from nearly spherical to highly elongated, and he speculated about the evolutionary relationships between different types. Scholars still argue whether ellipticals form primarily through the mergers of smaller galaxies, or whether some are born large from the direct collapse of primordial gas clouds. The truth, as with most cosmic questions, probably involves a messy combination of both scenarios, varying from galaxy to galaxy. A quirky historical footnote. Hubble initially thought the sequence from elliptical to spiral represented an evolutionary progression, with ellipticals being early types that would eventually flatten and sprout arms. This turned out to be backwards. Spirals are often the precursors, and ellipticals the end products of mergers that scramble orderly rotation into random stellar orbits. The terminology stuck, though, which is why you will still hear astronomers refer to ellipticals as early-type galaxies, even though they are often the oldest and most evolved structures in their clusters. So when we say IC1101 is the largest galaxy we have ever found, we need to be a little careful about what we mean. By diameter, IC1101 is almost certainly among the top contenders, possibly the outright winner depending on where you draw the edge. By stellar mass, it is staggeringly heavy, home to an estimated 100 trillion stars, roughly 1,000 times more than the Milky Way. By volume, its elliptical shape gives it a commanding lead over any spiral of comparable width, and by the extent of its dark matter halo, it may stretch even further, a gravitational sphere of influence reaching millions of light years in every direction. But there are rivals. Recent discoveries have uncovered radio galaxies with jets and lobes extending even further than IC1101's stellar halo. Alcyonius, discovered in 2022, boasts radio structures spanning nearly 17 million light-years, though the galaxy itself is far smaller. Does that count? If you measured IC 1101 by the influence of its central black hole's jets rather than its stars, it might grow larger still. The debate is ongoing, and astronomers love a good debate. It keeps conferences lively and graduate students employed. For our purposes tonight, we will focus on IC 1101 as a coherent gravitational object, a collection of stars, gas and dark matter bound together by mutual attraction. By that standard, IC 1101 remains the reigning champion, a cosmic heavyweight whose sheer bulk is difficult to exaggerate. And even if some future telescope reveals a larger competitor lurking in a distant corner of the observable universe, IC 1101 will still hold a special place in the history of astronomy as the galaxy that first showed us just how big could get. You let this idea settle into your mind like sediment drifting to the bottom of a still pond. The universe contains structures of almost incomprehensible scale, and yet it also contains you, a tiny assembly of atoms somehow capable of contemplating the whole. There is a strange comfort in that asymmetry. You do not need to be large to appreciate largeness. You do not need to last forever to marvel at things that have burned for billions of years. You just need to be here, now, drifting in the dark with your thoughts, letting the numbers wash over you without demanding that they make sense in any practical way. And speaking of numbers, let us talk about IC 1101's specific dimensions in a little more detail, because the sheer scale deserves a proper attempt at visualization, even if visualization is ultimately doomed to fail. After all, failure can be its own kind of fun, especially when you are half asleep and the stakes are purely imaginary. The soft hum of your imaginary spacesuit's life support systems fills your ears, a gentle white noise that blends with the silence of the void. Ahead, somewhere impossibly far away, Orca 1101 waits, a faint smudge in the cosmic distance, a lantern the size of a small universe. You nudge yourself forward, knowing you will never arrive, but enjoying the journey nonetheless. You have been drifting for what feels like hours, though time out here is a slippery concept, measured more in heartbeats than in seconds. The Milky Way is now so far behind you that it has become just another anonymous sparkle in a sky crowded with sparkles, indistinguishable from the billions of other galaxies scattered across the observable universe. Ahead, you notice the faintest hint of a glow, a soft, diffuse smudge that seems to occupy more space than any single star should. That smudge is your destination, and it has a name, IC 1101. The designation sounds clinical, almost bureaucratic, like a form you might fill out at a government office. IC stands for Index Catalogue, a supplement to the older New General Catalogue that astronomers compiled in the late 19th century to keep track of the growing number of fuzzy objects discovered through increasingly powerful telescopes. The number 1101 simply means it was the 1101st entry in that particular list. There is no poetry in the name, no mythology, no ancient story of gods or heroes, just a catalogue number assigned by careful methodical observers who had no idea they were labelling one of the most extraordinary objects in existence. IC 1101 was first recorded by the British astronomer John Lewis Emile Dreyer, who compiled the Index Catalogue between 1888 and 1907. Dreyer himself probably never realised the true nature of what he was cataloguing. At the time, the so-called spiral nebulae were still the subject of fierce debate. Were they clouds of gas within our own Milky Way, or were they entire island universes far beyond our galaxy's borders? It was not until the 1920s, when Edwin Hubble measured the distance to the Andromeda Nebula using Cepheid variable stars, that the extragalactic nature of these objects became undeniable. By then, IC 1101 was just another faint entry in a long list, waiting for future generations to recognise its significance. You approach the region of space where IC 1101 resides, and the first thing you notice is that it does not sit alone. It is the central, dominant member of a galaxy cluster called Abell 2029. Galaxy clusters are the largest gravitationally bound structures in the universe, collections of hundreds or thousands of galaxies held together by mutual attraction. Abell 2029 is named after George Abell, an American astronomer who spent years photographing the sky and identifying these cosmic cities in the mid-20th century. His catalogue, published in 1958, remains one of the foundational references for cluster studies. Abell 2029 lies roughly 1 billion light-years from Earth, in the direction of the constellation Virgo as seen from our planet. At that distance, the light now entering our telescopes began its journey when life on Earth was still confined to the oceans, when the most complex organisms were things like jellyfish and worms. 1 billion years is long enough for continents to drift, for species to rise and fall, for entire ecosystems to be rewritten from scratch. And yet, from the perspective of the universe, 1 billion years is almost casual, a modest fraction of the cosmos's nearly 14 billion year history. As you draw closer to Abell 2029, you see galaxies everywhere. They cluster and swarm like fireflies on a summer night, their light blending into a collective glow that suffuses the cluster's core. But one galaxy dominates all others. It sits at the gravitational centre, a vast glowing ellipse that dwarfs its neighbours the way a cathedral dwarfs the houses surrounding it. This is IC1101, and even from a distance you can sense its mass, a gravitational presence so powerful that it has pulled everything else in the cluster toward it. The preliminary numbers are enough to induce a quiet gasp. Early estimates suggested IC1101 might span anywhere from 4 to 6 million light-years across, though these figures have been refined and debated endlessly since. For comparison, the Milky Way is about 100,000 light-years in diameter. That means IC1101 could be 40 to 60 times wider than our home galaxy. If you place the Milky Way at the centre of IC1101, it would be a small coin lost in a vast ocean of stars, barely noticeable amid the trillions of other suns. Stellar mass estimates are equally staggering. IC1101 may contain as many as 100 trillion stars, roughly 1,000 times the Milky Way's count. Each of those stars is a sun, many larger and brighter than our own, many smaller and dimmer, all fusing hydrogen into helium in their cores, all contributing their tiny share to the galaxy's collective glow. If you tried to count IC1101 stars at a rate of 1 per second, you would need over 3 million years to finish, and that assumes you never slept, never paused, never lost your place. The task is not just impractical, it is cosmically absurd, a quirky detail that astronomers find endlessly fascinating. IC1101's colour is distinctly yellow-orange, the hue of an ageing stellar population. Young galaxies tend to blaze blue with the light of hot, massive stars that burn fast and die young. Older galaxies, especially giant ellipticals like IC1101, have exhausted most of their star-forming gas and are now populated primarily by long-lived, lower-mass stars that glow in warmer tones. The colour tells a story. IC1101 is old, settled, its days of furious star formation largely behind it. It is a galaxy in its twilight, though that twilight will last for billions of years yet. There is ongoing scholarly debate about exactly how old IC1101 is and how it reached its current size. Some researchers believe it formed relatively early in cosmic history and has been steadily accreting smaller galaxies ever since, growing fat on a diet of cosmic cannibalism. Others suggest it may have experienced one or more major mergers with comparably sized galaxies, events that would have scrambled any original structure and puffed up the combined remnant into the bloated ellipse we see today. The truth probably involves both processes, a long history of eating smaller neighbours punctuated by occasional dramatic collisions. You float in silence, contemplating the sheer improbability of what lies before you. A structure this large should not feel so serene. There should be chaos, turbulence, some visible sign of the violence required to assemble so much matter in one place. but IC 1101 glows peacefully, its stars orbiting the common centre of mass in slow, stately paths, its gravity holding everything in place with effortless authority. The violence is there, of course, but it happened long ago, and the scars have faded into the smooth, featureless glow of an ancient elliptical. You take a moment to appreciate the silence. Out here there is no sound, no rustle of wind, no hum of traffic, nothing but the soft rhythm of your own breathing inside your imaginary helmet. The galaxy before you is a monument to time and gravity, a cathedral built by the patient accumulation of matter over eons, and you, improbably, are here to witness it, even if only in imagination, even if only for a few minutes before sleep pulls you under. Ahead, the core of IC 1101 beckons, a brighter region where stars crowd closer together and something truly massive lurks in the darkness. But that is a story for the next stretch of our journey. For now, simply rest in the approach, letting the scale of IC 1101 settle into your bones like warmth from a distant fire. The glow of IC 1101 fills your field of vision now, a soft amber haze that seems to have no edges, no boundaries, just a gradual fading into the black of intergalactic space. You try to hold the whole thing in your mind, to picture it as a single object with a defined shape and size, but your imagination keeps sliding off the surface like water off polished stone. This is the problem with cosmic scales. Human brains evolved to track threats on the savannah, to estimate distances measured in footsteps, to remember the locations of fruit trees and watering holes. Nothing in your evolutionary history prepared you to visualize 4 to 6 million light years. So let us try a different approach. Let us stack Milky Ways. You summon a mental image of our home galaxy, that elegant spiral you left behind so long ago. It measures roughly 100,000 light years across, a respectable size by galactic standards, enough room for several 100 billion stars and all the planets, moons, asteroids and comets that accompany them. Now imagine placing a second Milky Way next to the first, edge to edge. You have doubled the span to 200,000 light years. Add a third, a fourth, a fifth. At 10 Milky Ways, you reach 1 million light years, still well short of IC 1101's minimum estimated diameter. Keep going. 20 Milky Ways, 30, 40, somewhere around 40 to 60 copies depending on whose measurements you trust. You finally approach the width of IC 1101, 40 to 60 entire Milky Way galaxies, each one containing hundreds of billions of stars, laid end to end like coins on a table, and you still have only matched the diameter of a single, monstrous elliptical. The Milky Ways vanish into IC 1101 like pebbles tossed into a lake, absorbed without a ripple, utterly insignificant. A mainstream historical fact to anchor this visualization. The first reasonably accurate measurement of the Milky Way's size came in the early 20th century, when Harlow Shapley used the distribution of globular clusters to estimate the galaxy's extent and our Sun's position within it. Shapley's work revolutionized our understanding of cosmic geography, showing that we were not at the center of the galaxy but rather off to one side, orbiting a distant core. His estimates were rough by modern standards, but they established the basic scale that later observations refined. Without Shapley's groundwork, we would not have the benchmarks needed to appreciate just how absurdly large IC 1101 truly is. Now let us try another comparison, one involving time rather than space. Light travels at about 300,000 kilometers per second, the cosmic speed limit that nothing with mass can exceed. At that pace, light can circle the Earth more than 7 times in a single second. It reaches the Moon in a little over 1 second, the Sun in about 8 minutes, and the outer planets in a few hours. These are distances humans can almost grasp, scaled-up versions of the journeys we make on Earth. But light needs about 100,000 years to cross the Milky Way. That is a span of time roughly equal to the entire existence of anatomically modern humans. Every migration, every empire, every language, every war, Every love story that has ever occurred in our species' history fits inside the time it takes light to traverse our galaxy once. And IC1101, light needs 4 to 6 million years, minimum, to make the same journey. That is longer than the genus Homo has existed. That is deep into the era of Australopithecus, the small-brained ancestors who walked upright on the African plains, but had not yet learned to chip stones into tools. You float in the amber glow, letting these numbers tumble through your mind like smooth river stones. 4 to 6 million light years. It is a phrase that sounds almost manageable when spoken quickly, a handful of syllables that slip off the tongue. But the reality behind those syllables is so vast that it defies honest comprehension. All you can do is approach it from different angles, chip away at its edges with analogies and comparisons, and hope that something resembling understanding begins to crystallize in the gaps. A quirky tidbit to lighten the mood. If you tried to send a text message across IC1101 using conventional radio signals, which travel at the speed of light, you would wait 4 to 6 million years for the message to arrive. The reply, assuming anyone was there to receive it and respond instantly, would take another 4 to 6 million years to get back. By the time you heard LOL, entire species would have evolved and gone extinct on Earth. Texting across IC1101 makes long-distance relationships look trivially convenient. Astronomers still argue about the precise boundaries of IC1101, because defining the edge of a galaxy is surprisingly philosophical. Stars do not simply stop at a line. They thin out gradually, their density dropping as you move away from the centre. At some point, the stellar density becomes so low that you're effectively in intergalactic space, but there is no sharp transition, no fence marking the property line. Some researchers set the boundary at a certain surface brightness threshold. Others include the faint halo of old stars that surrounds many galaxies. Still others factor in the dark matter halo, which extends far beyond the visible stars. Depending on which definition you use, IC1101's diameter can vary by millions of light years. The conservative estimates stick to the region where stars are relatively abundant, yielding figures around 4 million light years. The more generous estimates include the outer halo and dark matter envelope, pushing the number towards 6 million or beyond. Both approaches have merit, and both have drawbacks. The debate is less about who is right and more about which definition is most useful for a given scientific question. For our purposes, the exact number matters less than the general impression. IC1101 is so large that it strains the very concept of galaxy to its breaking point. It is less a single object and more a gravitational empire, a region of space where the collective pull of 100 trillion stars dominates the local fabric of space-time. If galaxies were countries, IC1101 would be a supercontinent, a landmass so vast that travellers crossing it would speak different languages at either end. You gaze into the glow, feeling a strange mixture of awe and drowsiness settling over you. The scale is humbling, almost oppressively so, and yet there is something soothing about surrendering to it. You do not need to contain IC1101 in your mind. You just need to acknowledge its existence, to let its immensity wash over you like a warm tide, and to accept that the universe is under no obligation to fit inside your understanding. That acceptance is its own kind of peace. Ahead, the stars grow denser, the light brighter. You are approaching the core of IC1101, where gravity packs matter together more tightly and where something very, very heavy waits in the darkness. But that is a journey for the next stretch. For now, simply rest in the vastness, counting Milky Ways like sheep until the numbers blur into a soft, endless glow. You drift closer to IC1101's heart, and the stars begin to crowd together in ways that feel almost claustrophobic, which is absurd given the distances involved. Even in the densest regions of this galaxy, individual stars are separated by light years, vast gulfs of emptiness that would take human spacecraft thousands of years to cross. But the visual impression is one of abundance, a sky so thick with suns that the darkness between them almost vanishes, replaced by a continuous golden glow. 100 trillion stars. That is the number astronomers have attached to IC 1101, though it comes with caveats and error bars and the usual scientific hedging. 100 trillion is a rough estimate derived from the galaxy's total luminosity and assumptions about the typical mass and brightness of its stellar population. The actual count could be higher or lower by tens of trillions, a margin of error that exceeds the entire stellar population of the Milky Way. But even the conservative lower bound is staggering, something like 50 trillion stars, still hundreds of times more than our home galaxy contains. Let us try to unpack that number. 100 trillion is written as a 1 followed by 14 zeros, 100 trillion. It is the kind of number that appears in national debt calculations and particle physics experiments, not in descriptions of countable objects like stars. And yet, there they are, burning steadily in the amber haze before you, each one a sphere of superheated plasma fusing lighter elements into heavier ones, each one radiating energy into the void, each one potentially orbited by worlds you will never see. The stars of AC 1101 are predominantly old. This is a hallmark of giant elliptical galaxies, which tend to exhaust their star-forming gas early, and then coast on their existing stellar population for billions of years. Young massive stars, the brilliant blue giants that blaze briefly and die spectacularly, are rare here. Instead, IC 1101 is dominated by stars like the Sun, or smaller, modest yellow and orange and red dwarfs that burn their fuel slowly and can shine for tens or hundreds of billions of years. The galaxy's overall colour reflects this demographic, a warm yellow-orange hue, the light of a mature stellar population that has long since settled into quiet middle age. A mainstream historical fact worth noting. Our understanding of stellar populations owes much to the work of Walter Baade, a German-born astronomer who worked at Mount Wilson Observatory during the mid-20th century. Baade distinguished between two types of stellar populations. Population 1, the younger, metal-rich stars found in the spiral arms of galaxies like the Milky Way, and Population 2, the older, metal-poor stars concentrated in galactic bulges and halos. IC 1101, as a giant elliptical, is dominated by Population 2 stars, ancient suns formed when the universe was younger and heavier elements were scarcer. Baade's classification system revolutionized stellar astrophysics and remains foundational today. Now, let us consider what those 100 trillion stars might mean for planets. The Milky Way contains somewhere between 100 billion and 400 billion stars, and recent surveys suggest that most of those stars host at least one planet. If we assume similar statistics for IC 1101, a big assumption given the different stellar population, then the galaxy could contain hundreds of trillions of planets. The number is so large that it loses meaning, becoming a kind of numerical fog that refuses to resolve into anything concrete. Among those potential hundreds of trillions of planets, how many might be habitable? How many might orbit their stars at just the right distance, with just the right atmospheric conditions to allow liquid water to pool on their surfaces? How many might host life, and of those, how many might have developed intelligence, curiosity, technology? These questions are scientifically legitimate but currently unanswerable. We have no way to survey IC 1101's planets directly. They are far too distant and far too faint for even our most powerful telescopes to detect. All we can do is speculate, running the numbers through probabilistic frameworks like the Drake equation, and hoping the assumptions are not too wildly off. A quirky tidbit that sometimes keeps astronomers awake at night. If even a tiny fraction of IC 1101's planets developed intelligent life, the galaxy could host civilizations numbering in the billions. And yet, we have detected no signals, no signs of megastructures, no evidence of anyone out there waving hello. This is a local version of the Fermi paradox, the puzzle of why, in a universe so vast and so old, we seem to be alone. Perhaps intelligent life is vanishingly rare. Perhaps it tends to destroy itself before achieving interstellar communication. Perhaps it is there but operating on principles we cannot recognize. The debate is ongoing, and the silence remains unbroken. You float among the stars of IC1101, or at least among your imagined version of them, and you try to picture what the sky might look like from a planet deep inside this galaxy. In the Milky Way, our night sky contains a few thousand stars visible to the naked eye, scattered unevenly across the dome of heaven. Near IC1101's core, the stellar density is so much higher that the night sky might be a continuous blaze of light, a dome of overlapping suns with no true darkness between them. Shadows might be soft and diffuse, cast by 1,000 sources at once. The concept of night might lose its meaning entirely. And yet, even in such a crowded sky, distances would remain immense. The nearest neighbouring star might still be several light years away, a journey of millennia for any spacecraft we could currently build. The stars would seem close, but they would be just as unreachable as ever, beautiful and aloof, burning in their own private fires. This is the paradox of cosmic abundance. More stars than you could ever count, and yet each one isolated by gulfs so wide they might as well be infinite. Scholars still argue about the stellar dynamics inside giant ellipticals like IC1101. Unlike spiral galaxies, where stars orbit the centre in relatively orderly disk-like paths, elliptical galaxies have stars moving in all directions, more like a swarm of bees than a carousel of horses. This randomized motion is thought to result from the mergers and collisions that built the galaxy over billions of years. Each merger scrambled the orbits of the incoming stars, mixing them with the existing population until all sense of organized rotation was lost. The result is a galaxy that looks serene from the outside but is, in a sense, a gravitational blender, its stars tracing chaotic paths through a shared potential well. You let your eyes, or whatever passes for eyes in this imaginary journey, rest on the glow around you. 100 trillion stars, each one a furnace, each one a story, each one utterly indifferent to your presence, burning because the laws of physics demand it, shining because there is nothing else for a star to do. The universe is not built for comfort, and yet, floating here in the imagined warmth of EC1101's light, you find a strange kind of peace. The stars do not know you exist, but you know they exist, and somehow that asymmetry is enough. Ahead, the light grows brighter still. You're approaching the core, where something far more massive than any star waits in the darkness, bending space-time around itself like a stone pressing into a rubber sheet. But that is the next stretch of the journey. For now, simply count stars, or rather, accept that you cannot count them, and let that acceptance carry you a little deeper into sleep. The stars around you have grown so numerous that they almost merge into a continuous glow, a celestial fog that seems to press against your senses from every direction. And yet, even as the light intensifies, you become aware of something ahead that is not light at all. It is an absence, a region where the glow subtly dims, where space-time itself seems to curve inward like water spiralling toward a drain. You have reached the heart of IC1101, and at that heart sits one of the most massive black holes ever discovered. Black holes are strange enough in concept, objects so dense that their gravity prevents even light from escaping, regions where the normal rules of physics twist into something unrecognizable. The Milky Way has its own supermassive black hole called Sagittarius A star, nestled at the galactic centre. It weighs roughly 4 million times the mass of the Sun, which sounds impressive until you consider what lurks inside IC1101. Estimates for IC1101's central black hole vary, but the most commonly cited figure places it somewhere between 40 billion and 100 billion solar masses. That is not a typo. We're talking about a black hole 10,000 to 25,000 times more massive than the one at the centre of our own galaxy. Let that sink in for a moment. 40 billion suns compressed into a region of space from which nothing can escape. The event horizon, the boundary beyond which escape becomes impossible, might stretch across a volume larger than our entire solar system. If you replace the Sun with IC 1101's black hole, the event horizon would extend well past the orbit of Neptune, swallowing all the planets, all the moons, all the asteroids and comets in a single silent gulp. And you would have no warning. There is no sign at the event horizon, no flash of light, no dramatic announcement. You simply cross a line, and from that moment on, your future contains only one destination. The singularity at the centre, where density becomes infinite and the laws of physics as we know them break down completely. A mainstream historical fact to anchor this cosmic horror: black holes were first predicted theoretically in 1916 by Karl Schwarzschild, a German physicist who solved Einstein's equations of general relativity while serving on the Russian front during World War I. Schwarzschild derived the mathematics describing a spherically symmetric gravitational field, and he noticed that at a certain radius, now called the Schwarzschild radius, the equations produced a singularity. Einstein himself was skeptical that such objects could exist in nature, dismissing them as mathematical curiosities. It took decades before astronomers found compelling evidence that black holes were real, and supermassive black holes at galactic centres were not confirmed until the late 20th century. You drift closer to the darkness at a C1101's core, feeling the tug of gravity strengthen with each passing moment. Of course, in this imaginary journey you are perfectly safe. The physics here bends to storytelling rather than general relativity. But even in imagination, there is something unsettling about approaching a region where space-time itself becomes a one-way street. The light from stars behind you begins to warp, their images stretching and smearing as the black hole's gravity bends their photons into curved paths. This effect, called gravitational lensing, creates halos and arcs of light around massive objects, and near a black hole of this magnitude, the distortion is extreme. A quirky tidbit to lighten the mood: if you could somehow hover just outside the event horizon of IC 1101's black hole and wave to a friend far away, they would see you moving in extreme slow motion, your gestures stretched across years or centuries by the time dilation effects of intense gravity. Meanwhile, from your perspective, time would pass normally, but the universe outside would seem to speed up, stars being born and dying in what felt like moments. You and your friend would be living in different temporal realities, separated not just by space, but by the warping of time itself. The black hole at a C1101 centre is classified as an ultramassive black hole, a term reserved for the most extreme examples known to science. Astronomers still argue about how such monsters form. One possibility is that they grow gradually, accreting gas and swallowing stars over billions of years, steadily adding mass like a snowball rolling downhill. Another possibility is that they form from the mergers of smaller supermassive black holes, combining when their host galaxies collide. A third, more speculative scenario suggests that some ultramassive black holes formed early in the universe's history, from the direct collapse of enormous gas clouds, skipping the intermediate stages of stellar black holes entirely. Each scenario has implications for IC 1101's history. If the black hole grew primarily through accretion, the galaxy must have funneled vast quantities of gas toward its centre over cosmic time, feeding the beast through mechanisms we are still working to understand. If it grew through mergers, IC 1101 must have experienced multiple major collisions with other large galaxies, each collision delivering a new supermassive black hole to be absorbed. The truth probably involves some combination of all three processes, a messy, violent history hidden beneath the serene glow of the galaxy's present-day appearance. As you hover near the event horizon, safely, impossibly, imaginarily, you sense the sheer indifference of the black hole. It does not care about you, It does not care about the trillion stars orbiting around it. It is simply a concentration of mass and space-time curvature, obeying the equations of general relativity with perfect fidelity. There is no malice in its gravity, no intent in its consumption of light. It is a feature of the cosmos, as natural as a mountain or a river, just operating on scales that make mountains and rivers seem like grains of sand. And yet, there is something almost comforting about that indifference. The black hole will not judge you. It will not ask anything of you. It simply exists, a anchor at the heart of a vast galactic empire, holding 100 trillion stars in its gravitational embrace. You can rest in its presence without fear, knowing that in this imaginary journey, no harm can come to you. The darkness is just darkness. The gravity is just gravity. And you're just a mind floating through a story drifting towards sleep. You begin to pull back from the core, letting the stars brighten around you again as the black hole recedes into the background. There is more to explore in IC 1101, more layers to peel back, more mysteries to ponder. But the heart has been acknowledged, the monster glimpsed. Whatever else this galaxy holds, it is all orbiting that central darkness, dancing around an absence that defines everything. You drift outward from the core, leaving the supermassive black hole behind, and the stars begin to spread apart once more, their density thinning as you move toward IC 1101's outer reaches. The glow around you softens from a blazing amber to a gentler gold, and you have a moment to contemplate the nature of the structure you're floating through. IC 1101 is not a spiral galaxy like the Milky Way. It is an elliptical, a fundamentally different kind of stellar city, and understanding that difference is key to appreciating how this cosmic giant came to be. Spiral galaxies are what most people picture when they hear the word galaxy. They have beautiful sweeping arms that curl outward from a central bulge, lanes of dust and gas threading between the stars, regions of active star formation blazing blue with young, hot suns. The Milky Way is a spiral, as is our nearest large neighbour Andromeda. Spirals are dynamic, constantly churning, their arms maintained by density waves that ripple through the disk like slow-motion sound waves. They are galaxies in motion, galaxies with visible structure, galaxies that seem to be going somewhere. Ellipticals, by contrast, are galaxies that have arrived. They are smooth, featureless blobs of stars, ranging from nearly spherical to elongated like footballs, with no spiral arms, no dust lanes, no obvious signs of recent star formation. Their stars move in random, criss-crossing orbits rather than the orderly rotation of a disk. They glow with the warm light of old stellar populations, yellows and oranges and reds, the colours of suns that have been burning for billions of years. Ellipticals are often described as dead galaxies, though that term is misleading. They are not dead so much as settled, mature, having exhausted the gas and dust that would fuel new star birth. IC 1101 is a supergiant elliptical, the most massive subclass of an already massive category. Supergiant ellipticals are rare, found almost exclusively at the centres of large galaxy clusters, where they have grown fat on the accumulated matter of their cosmic neighbourhoods. They are the end products of a violent history, their smooth appearances hiding billions of years of mergers, collisions and gravitational cannibalism. A mainstream historical fact. The classification of elliptical galaxies was formalised by Edwin Hubble in his famous tuning fork diagram, published in 1936. Hubble sorted ellipticals by their apparent shape, from E0, nearly spherical, to E7, highly elongated. He originally thought this sequence represented an evolutionary progression, with galaxies starting as ellipticals and gradually flattening into spirals. This turned out to be wrong. If anything, the evolution runs in the opposite direction, but Hubble's classification system remains in use today, a testament to its practical utility, even as our theoretical understanding has changed. The key to understanding elliptical galaxies is mergers. When two spiral galaxies collide, the gravitational interaction scrambles the orderly rotation of their disks. Stars that once orbited peacefully in flat planes are flung onto chaotic, random trajectories. The gas and dust that fueled star formation is either consumed in a burst of new stellar births or heated so intensely that it escapes the merged system entirely. What remains is a puffed-up randomized collection of stars, an elliptical galaxy. IC 1101, being as massive as it is, has clearly experienced many such mergers. Simulations suggest that a galaxy of its size could not have formed from a single, primordial gas cloud. It must have assembled over billions of years through the steady accretion of smaller galaxies. Each merger added mass, scrambled orbits, and erased a bit more of whatever original structure the component galaxies might have had. The result is the smooth, serene giant you see before you, a galaxy that looks peaceful but is, in a sense, a graveyard of absorbed victims. A quirky tidbit. Some astronomers have compared elliptical galaxies to retirement communities for stars. The frantic activity of youth, the star formation, the supernova explosions, the dramatic spiral arms, has given way to a quiet, settled existence. The stars of IC 1101 are not doing anything particularly exciting. They are just burning, orbiting, waiting out the trillions of years until their fuel runs out. It is not a bad existence, just a calm one. Scholars still argue about the precise formation pathways of supergiant ellipticals like IC 1101. Some models suggest they form early in cosmic history, when the universe was denser and mergers were more frequent, and then grow slowly through minor accretion events ever since. Other models propose that the largest ellipticals continue to experience major mergers, even at relatively recent cosmic times, events that would inject fresh stellar populations and temporarily reignite star formation. The fossil record is ambiguous, and different galaxies may have followed different paths to their current states. What is clear is that IC 1101's elliptical nature is intimately connected to its enormous size. Spiral galaxies have a kind of upper limit to their growth. Beyond a certain mass, they become gravitationally unstable, and tend to form bars or other structures that disrupt the elegant spiral pattern. Ellipticals face no such constraint. They can keep growing, absorbing more and more mass, their randomized stellar orbits accommodating new arrivals without any need for structural reorganization. IC 1101 has exploited this freedom to become something truly extraordinary, a galaxy so large it challenges our very definition of the category. You float through the golden haze, watching stars drift past like snowflakes in a slow-motion blizzard. There is no urgency here, no drama, just the patient accumulation of billions of years. IC 1101 did not become the largest galaxy through any single dramatic event. It became the largest through persistence, through the steady, relentless pull of gravity, drawing more and more matter into its embrace. It is a lesson in cosmic patience, a reminder that the universe operates on timescales that make human history seem like a single breath. Ahead, the glow continues, seemingly endless. You have crossed only a fraction of IC 1101's diameter, and already the journey has taken what feels like hours. But there is no need to rush. The galaxy will still be here, burning softly in the darkness, long after you have drifted off to sleep. You continue your drift through IC 1101, and as you move, you become aware of faint structures embedded in the otherwise smooth stellar glow. They are subtle, easy to miss if you're not looking for them. Streams of stars that seem to flow in particular directions, shells and arcs of slightly different brightness, regions where the stellar population is a shade more blue or a shade more red than its neighbours. These are the scars of IC 1101's violent past, the forensic evidence of the galaxy as it has consumed over billions of years. Galactic cannibalism is a real and ongoing process in the universe. When a large galaxy encounters a smaller one, gravitational forces gradually tear the smaller galaxy apart, stretching it into long, thin streams of stars that eventually mix into the larger galaxy's population. The process can take billions of years, but the evidence persists for even longer, preserved in the positions and motions of individual stars. Astronomers call these features tidal streams and stellar shells, and they are found around most large galaxies, silent witnesses to past meals. IC1101 has clearly eaten well. The sheer mass of the galaxy implies that it has absorbed hundreds, possibly thousands of smaller galaxies over its lifetime. Each victim contributed its stars to the collective glow, its gas to the central black hole, its dark matter to the encompassing halo. The victims are gone now, their individual identities erased, but traces remain for those who know how to look. A mainstream historical fact, the study of tidal streams and stellar shells accelerated in the late 20th century as telescopes became sensitive enough to detect these faint structures. The Milky Way itself is surrounded by streams from disrupted dwarf galaxies, most famously the Sagittarius Stream, a ribbon of stars wrapping around our galaxy that was discovered in 1994. These features transformed our understanding of galactic evolution, showing that even our own galaxy is an active predator, growing by devouring its neighbours. In IC1101's case, the evidence of past mergers is particularly striking because of the galaxy's size. To reach its current mass, IC1101 must have experienced not just minor accretion events, but also major mergers with other substantial galaxies. These collisions would have triggered temporary bursts of star formation, as gas clouds compressed and collapsed, injecting younger stellar populations into the predominantly old galaxy. Some astronomers have detected hints of such populations in IC1101's spectral signatures, though the evidence remains debated. A quirky detail that fascinates researchers: the stars stripped from different galaxies carry distinct chemical fingerprints. Each galaxy has its own history of supernova explosions and stellar nucleosynthesis, producing a unique mix of heavy elements that gets incorporated into subsequent generations of stars. By measuring these abundances, astronomers can sometimes trace individual streams back to their parent galaxies, piecing together a menu of IC1101's past meals. It is forensic astronomy at its finest, reconstructing crimes that happened billions of years ago. You pass through one of these faint streams, though in your imaginary journey, it is indistinguishable from the surrounding stars. The stream might contain millions or billions of suns, the remains of a galaxy that was once a thriving stellar city in its own right. Perhaps it had planets, perhaps it had life. Now it is just a smear of light, a ghost absorbed into the body of its devourer. The universe is not sentimental about such things. Gravity simply does what gravity does, and the strong consume the weak. Scholars still argue about the rate of IC1101's growth. Some models suggest that most of the mass accumulation happened early, within the first few billion years of the galaxy's existence, when the universe was denser and encounters were more frequent. In this picture, IC1101 has been relatively quiet for the past several billion years, its growth slowing as the cosmic expansion spread galaxies further apart. Other models propose that significant mergers have continued until relatively recently, perhaps within the last billion years, events that would leave detectable signatures in the galaxy's stellar populations and kinematics. The truth is probably somewhere in between. IC1101 likely experienced its most dramatic growth early, when the Abell 2029 cluster was still assembling and galaxies were falling into the central potential well in large numbers. But even today, minor accretion events continue. Small galaxies that wander too close to IC1101 are captured and gradually torn apart, their stars added to the ever-growing census. The galaxy is not done eating. It has simply moved from a diet of large meals to a steady snacking. You think about what this means for any civilizations that might have existed in IC1101's victims. Entire galactic ecosystems, potentially harbouring trillions of planets, have been absorbed into this giant over cosmic time. If any of those planets developed intelligent life, that life would have experienced something truly strange. A sky that slowly changed over millions of years, their home galaxy stretching and distorting as gravitational forces tore it apart. New stars appearing from directions where none had been before. The transition would have been far too slow for any individual to notice, but over geological timescales, the transformation would have been complete. And then what? The stars of the devoured galaxy continue to shine, their planets continue to orbit, but now they belong to IC 1101. Any surviving civilizations would find themselves citizens of a new galactic empire, their old home erased, their new one incomprehensibly vast. It is a strange kind of immortality. The individual galaxy dies, but its components live on, scattered through the body of the cannibal. The universe recycles everything, even civilizations, even memories, even the sense of belonging to a particular patch of cosmic real estate. You drift on, leaving the faint tidal stream behind. The stars around you are peaceful now, their violent histories hidden beneath a calm and ancient glow. IC 1101 shows no obvious signs of ongoing turmoil. It is a galaxy in equilibrium, its mergers complete, its structure settled. But the scars are there, if you know where to look, whispering stories of absorption and transformation that stretch back to the earliest epochs of cosmic history. You find yourself wondering how humans ever managed to notice C1101 in the first place. 1 billion light-years is an absurd distance, so far that the light now reaching our telescopes began its journey when the most complex life on Earth was still figuring out how to crawl. And yet somehow, a species that evolved to hunt antelope on the African savanna developed the technology to detect, catalogue, and measure a galaxy larger than anything our ancestors could have imagined. The story begins, as so many astronomical stories do, with better telescopes. In the late 19th century, astronomers were busy cataloguing the thousands of faint fuzzy objects scattered across the sky. Many of these turned out to be nebulae, clouds of gas and dust within our own galaxy. But others stubbornly refused to resolve into individual stars, remaining smooth and featureless even under the highest magnifications. These objects, sometimes called spiral nebulae for their distinctive shapes, became the subject of intense debate. Were they part of the Milky Way, or were they something else entirely? IC 1101 was catalogued during this period, entered into the index catalogue by John Louis Emile Dreyer as just another faint smudge among thousands. Dreyer was a meticulous observer, but the tools of his era were limited. He had no way of knowing the true nature of what he was recording, no way of measuring the distances involved, no way of appreciating that this particular smudge would one day be recognized as the largest known galaxy in the universe. A mainstream historical fact, the debate over the nature of spiral nebulae was famously settled in 1920 during the Great Debate between astronomers Harlow Shapley and Heber Curtis. Shapley argued that the spiral nebulae were small, nearby objects within the Milky Way. Curtis countered that they were distant island universes, entire galaxies comparable to our own. The debate was ultimately resolved in favour of Curtis when Edwin Hubble measured the distance to the Andromeda Nebula in 1923 to 1924, using Cepheid variable stars as standard candles. Andromeda was clearly far outside the Milky Way, confirming that spiral nebulae were indeed separate galaxies. IC 1101, being an elliptical rather than a spiral, was not at the centre of this particular debate. But the resolution of the Great Debate transformed how astronomers viewed objects like IC 1101. If spiral nebulae were distant galaxies, then elliptical nebulae probably were too. The universe suddenly became much, much larger, filled with billions of stellar cities separated by vast intergalactic voids. Over the following decades, astronomers developed increasingly sophisticated methods for measuring galactic distances. Cepheid variables, type Ia supernovae, surface brightness fluctuations, the Tully-Fisher relation. Each technique added another rung to the cosmic distance ladder, allowing researchers to push their measurements further and further into the universe. IC1101's distance was gradually pinned down to roughly 1 billion light-years, placing it firmly in the realm of distant ancient objects. A quirky tidbit: the measurement of IC1101's size has been revised multiple times over the years. Early estimates were based on photographic plates that captured only the brightest central regions of the galaxy. As detectors improved, fainter outer regions became visible, and the estimated diameter grew. Some of the most dramatic upward revisions came in the 1990s and 2000s, when digital CCD cameras replaced photographic film and allowed astronomers to probe much fainter surface brightness levels. The galaxy that once seemed merely large was revealed to be genuinely enormous. Scholars still argue about the precise methods used to measure a C1101's size. Different studies have used different techniques: isophotral radii, half-light radii, total luminosity integrations, and have arrived at different conclusions. The spread in published values reflects genuine scientific uncertainty, not sloppiness or disagreement for its own sake. Measuring the size of a distant, diffuse object is genuinely difficult, and the edge of a galaxy is more of a philosophical concept than a physical boundary. What is clear is that IC1101 attracted serious attention once astronomers realised how exceptional it was. Papers began to appear, noting its position at the centre of a bell 2029, its unusual size, its massive black hole. IC1101 became a standard reference point in discussions of galactic extremes, the go-to example when someone wanted to illustrate just how big a galaxy could get. You think about the generations of astronomers who contributed to this understanding. Dreyer, dutifully recording a faint smudge without knowing what it was. Shapley and Curtis, debating the scale of the universe while IC1101 quietly waited to be understood. Hubble, providing the key that unlocked extragalactic astronomy. The countless observers who refined measurements, improved techniques, pushed the boundaries of what we could see. Each generation built on the work of the last, a slow accumulation of knowledge that mirrors IC1101's own slow accumulation of mass. There is something moving about this parallel. IC1101 grew by absorbing smaller galaxies, each one contributing its stars and gas and dark matter to the collective whole. Human knowledge of IC1101 grew by absorbing the contributions of individual researchers, each one adding observations and insights and corrections to the collective understanding. Both processes are slow, both are incremental, both are ultimately collaborative. The universe and our knowledge of it are shaped by the same patient accumulation. You drift on, carrying this thought with you. The stars of IC1101 burn around you, indifferent to the efforts humans have made to understand them, but the understanding matters, not to the stars but to us. We are a species that looks up, that asks questions, that builds telescopes and writes catalogues and debates the nature of faint smudges in the sky. IC1101 does not care that we have measured it, but we care, and that caring is part of what makes us human. Ahead, the journey continues. There are more mysteries to explore, more scales to contemplate, more reasons to feel small and awed and strangely grateful. But for now, simply rest in the knowledge that you are part of a species that noticed IC1101 at all, that named it and measured it and wondered about it across 1 billion light-years of darkness. You've been drifting through IC1101 for what feels like an eternity, and yet you know that the light you're swimming in began its journey over 1 billion years ago. This is one of the strangest aspects of astronomy. When you look at distant objects, you're not seeing them as they are, but as they were when the light left them. The further away something is, the deeper into the past you peer. IC1101, at roughly 1 billion light-years, is a window into an era when Earth was a very different place. 1 billion years ago, the supercontinent Rodinia was beginning to break apart. Life on Earth was entirely microbial, with the most complex organisms being simple algae and bacteria. Multicellular life would not emerge for hundreds of millions of years yet. The atmosphere had only recently accumulated enough oxygen to support aerobic metabolism. The planet was green with cyanobacteria, but empty of anything you would recognize as an animal or plant. When you look at IC 1101, you're seeing light that left the galaxy during this primordial chapter of Earth's history. A mainstream historical fact, the realization that looking far away means looking back in time, was one of the conceptual breakthroughs of early 20th century astronomy. Before Einstein's special relativity established the finite speed of light as a fundamental constant, the implications of cosmic distances were not fully appreciated. Once astronomers understood that light from distant galaxies took millions or billions of years to reach us, they realized they were not just mapping space but also time. Every deep image of the universe is a kind of archaeology, revealing layers of cosmic history stacked upon each other. Measuring the distance to IC 1101 is not straightforward. You cannot simply point a ruler across a billion light years. Instead, astronomers rely on a series of overlapping techniques, each one calibrated against the others, forming what is called the cosmic distance ladder. At the base of the ladder are nearby objects whose distances can be measured directly, using parallax, the apparent shift in position of a star as Earth moves around the Sun. For more distant objects, astronomers use standard candles, objects of known intrinsic brightness that can serve as cosmic mile markers. Cepheid variable stars were the first widely used standard candles. These are pulsating stars whose brightness varies in a regular pattern, and the period of the pulsation is directly related to the star's true luminosity. By measuring the period and comparing the apparent brightness to the inferred true brightness, astronomers can calculate the distance. Cepheids are visible out to tens of millions of light years, far enough to reach nearby galaxies, but not nearly far enough to reach IC 1101. For more distant objects, astronomers turn to type Ia supernovae. These are explosions that occur in binary star systems, and they have a remarkably consistent peak brightness. By observing a type Ia supernova in a distant galaxy and measuring how bright it appears, astronomers can infer the galaxy's distance. Type Ia supernovae are bright enough to be seen across billions of light years, making them essential tools for measuring the most distant structures. A quirky detail: the consistency of type Ia supernovae is not perfect. There is a small spread in their peak luminosities, and correcting for this spread requires careful calibration. Astronomers have developed empirical relationships between the supernova's light curve shape and its true brightness, allowing them to standardize the candles. But uncertainties remain, and debates about the exact calibration of the type Ia supernova scale continue to this day. The distance to IC 1101, like the distances to most remote galaxies, carries error bars that reflect these ongoing uncertainties. Beyond supernovae, astronomers also use a technique called surface brightness fluctuations. In a nearby galaxy, individual stars can be resolved, and their brightness varies randomly from pixel to pixel in an image. In a more distant galaxy, the stars blur together, and the fluctuations smooth out. By measuring how smooth or grainy a galaxy's image appears, astronomers can estimate its distance. This technique is particularly useful for elliptical galaxies like IC 1101, which lack the distinctive spiral structure that makes other methods easier to apply. Scholars still argue about the best way to measure distances to very remote objects. Different techniques sometimes give slightly different answers, and reconciling these discrepancies is an ongoing challenge. The distance to IC 1101 is usually quoted as approximately 1 billion light-years, but this figure could be off by tens of millions of light-years in either direction. In cosmic terms, this uncertainty is small, but it matters when you're trying to calculate the galaxy's true size and mass. And this brings us to a deeper puzzle. How do you measure the size of something whose edge is not clearly defined? Stars do not stop abruptly at the border of AC1101. They thin out gradually, their density dropping until you're effectively in intergalactic space. But there is no hard boundary, no line on a map. Astronomers have developed various conventions for defining galactic size: isophotal radii, half-light radii, virial radii, but each convention gives a different answer. The isophotal radius is the distance at which the galaxy's surface brightness drops below a certain threshold. This threshold is arbitrary, chosen for convenience, and changing it can make a galaxy appear much larger or smaller. The half-light radius is the radius that encloses half of the galaxy's total light. This is a more physically meaningful measure, but it still depends on how you define total light in an object that fades gradually into the background. The virial radius is the radius within which the galaxy's gravity dominates over the cosmic expansion, a measure that includes dark matter and extends far beyond the visible stars. IC1101's commonly cited diameter of 4 to 6 million light-years is based on various combinations of these measures. The lower end reflects conservative estimates using the visible stellar distribution. The higher end includes the extended halo and dark matter envelope. Both numbers are legitimate, and both tell you something true about the galaxy. The debate is not about which is correct, but about which is most useful for a given scientific question. You float in this ambiguity, surrounded by stars whose exact boundary you cannot define, observing light that left its source 1 billion years before you existed. The universe does not come with labels and rulers. It comes with gradients and uncertainties, with edges that blur into backgrounds, with measurements that depend on how you choose to look. And yet, even with all these complications, we have managed to learn something true about IC1101. We know it is enormous. We know it is ancient. We know it is there, burning softly in the darkness, waiting for better telescopes and sharper techniques to reveal ever more of its secrets. You've been thinking of IC1101 as the undisputed champion, the largest galaxy ever found, and in many ways that title is deserved. But the universe is vast, and the quest to identify the biggest things in it is ongoing. As you drift through IC1101's amber glow, you become aware of whispers from other corners of the cosmos, rival titans that challenge IC1101's claim to the throne, or at least force us to ask what largest really means. Consider Alcyonius, a galaxy discovered in 2022 that sent ripples through the astronomical community. Alcyonius is a radio galaxy, meaning it possesses enormous jets of plasma blasting from its central black hole, extending far into intergalactic space. These jets, along with the giant lobes of radio-emitting material at their ends, stretch across a staggering 16 to 17 million light-years. If you count the radio lobes as part of the galaxy, Alcyonius is far larger than IC1101. But should you count them? A mainstream historical fact. Radio galaxies have been known since the mid-20th century, when astronomers first detected powerful radio emissions from objects later identified as distant galaxies with active nuclei. The mechanisms powering these jets involve supermassive black holes, accretion disks, and magnetic fields that accelerate particles to near the speed of light. The jets can extend for millions of light-years, far beyond the stars of the host galaxy, sculpting enormous cavities in the surrounding intergalactic medium. The problem with including radio lobes in a galaxy's size is that they are not gravitationally bound structures in the same way stars and dark matter halos are. The lobes are diffuse clouds of relativistic plasma, gradually expanding and fading as they lose energy to the surrounding environment. They are products of the galaxy rather than parts of it, more like exhaust from an engine than components of the engine itself. If you counted them, you would also have to count the wakes of material left behind by galaxies as they move through cluster gas, and then the definition of galaxy size becomes almost meaningless. Alcyonius's host galaxy, the collection of stars and dark matter at its centre, is actually rather modest, comparable to the Milky Way in stellar mass and diameter. It is the jets that make Alcyonius exceptional, not the galaxy itself. By the traditional definition of galactic size, Alcyonius is nowhere near C1101. By the radiolobe definition, it is far larger. The debate continues. Another challenger is Hercules A, another radio galaxy with jets extending roughly 1.5 million light-years. Hercules A's jets are particularly dramatic, displaying beautiful looping structures that suggest the black hole's orientation has wobbled over time, spraying plasma in different directions like a spinning garden hose. Hercules A is smaller than Alcyonius, but still impressive, and its jets raise the same definitional questions. Then there is Phoenix A, located at the centre of the Phoenix cluster, one of the most massive and most actively star-forming galaxy clusters known. Phoenix A is a monster in its own right, with an estimated stellar mass rivaling or exceeding us as C1101s, and a supermassive black hole that may weigh over 100 billion solar masses. Some researchers argue that Phoenix A has already surpassed C1101 in total mass, making it the new heavyweight champion. But the measurements are uncertain, and the comparison depends heavily on which mass estimates you trust. A quirky detail: the Phoenix cluster is named for the Phoenix constellation, but it could just as well be named for the mythical bird's habit of rising from the ashes. The cluster is experiencing an extraordinary burst of star formation, thousands of solar masses of new stars being born each year, fueled by cooling gas at the cluster's core. This makes Phoenix A unusual among giant ellipticals, which typically have little ongoing star formation. Whether this burst will continue or is just a temporary flare remains to be seen. Scholars still argue about whether IC1101 or Phoenix A holds the title of largest galaxy. The answer depends on how you define largest and which measurements you accept. By stellar mass, Phoenix A may have a slight edge, though the error bars overlap. By diameter, IC1101 probably wins, though Phoenix A is also enormous. By the mass of the central black hole, the competition is fierce, with both galaxies hosting ultramassive holes in the tens to hundreds of billions of solar masses. The truth is that crowning a single, largest galaxy may be a fool's errand. Galaxies come in different types, with different structures and different extents. Comparing an elliptical like IC1101 to a radio galaxy like Alcyonius is like comparing a watermelon to a vine. They are different kinds of objects, and the comparison depends on what you choose to measure. The leaderboard shifts depending on the criteria, and new discoveries keep reshuffling the rankings. You drift through IC1101 contemplating these rivals, and you realise that the competition itself is part of what makes astronomy exciting. There is always something bigger, something stranger, something that challenges our previous notions of what is possible. IC1101 held the crown for decades, and it may continue to hold it for decades more. Or tomorrow, a new survey might reveal a galaxy so large it makes IC1101 look ordinary. The universe has no obligation to respect our superlatives. For now, IC1101 remains the standard reference for the largest known galaxy, at least by the traditional measures of stellar mass and gravitational extent. It is the benchmark against which newcomers are compared, the giant that others must dethrone. And even if it is eventually surpassed, IC1101 will retain its historical importance as the galaxy that first showed us just how enormous a stellar city could grow. You let this thought settle into your mind like a warm blanket. The rankings do not really matter, not in any deep sense. What matters is the sheer improbability of any of this existing at all. Galaxies of any size, stars of any number, a universe that bothers to be at all. IC1101 is not significant because it is the largest. It is significant because it is, and because you are here to know about it, and because that knowing is itself a small miracle in a cosmos that did not have to include knowers. You have been swimming through IC1101's visible stars, but now you become aware of something else, something that does not glow, does not emit light, does not interact with your senses in any direct way. It is the dark matter halo. the invisible scaffolding that surrounds and permeates the galaxy, holding everything together through gravity alone. You cannot see it, but you can feel its effects. The way the stars move a little faster than they should. The way the galaxy holds its shape against the tug of cosmic expansion. Dark matter is one of the great mysteries of modern physics. We know it exists because of its gravitational effects. Galaxies rotate too fast. Clusters hold together too tightly. The cosmic web has too much structure, all pointing to an unseen mass that outweighs ordinary matter by roughly 5 to 1. But we do not know what dark matter is. It does not emit, absorb, or scatter light. It passes through ordinary matter like a ghost through a wall. Decades of experiments have failed to detect dark matter particles directly, leaving us with a gravitational fingerprint but no smoking gun. IC1101's dark matter halo is immense. Simulations suggest that the halo extends far beyond the visible stars, forming a roughly spherical envelope that might stretch tens of millions of light years in diameter. The exact extent is uncertain, because dark matter is, by definition, invisible. Astronomers infer its presence by measuring the motions of stars and satellite galaxies, by observing gravitational lensing effects, by comparing observations to theoretical models. The picture that emerges is of a galaxy embedded in a cocoon of darkness, the visible stars representing only a small fraction of the total mass. A mainstream historical fact, the existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who noticed that galaxies in the Coma cluster were moving too fast to be held together by their visible mass alone. Zwicky coined the term dunkle Materie, or dark matter, and estimated that the cluster must contain far more mass than meets the eye. His idea was largely ignored for decades, until the work of Vera Rubin and Kent Ford in the 1970s showed that the rotation curves of spiral galaxies also required invisible mass. Today, dark matter is a cornerstone of cosmology, even though its fundamental nature remains unknown. You float in IC1101's halo, sensing the presence of something vast and formless around you. It is a strange sensation, knowing that most of the mass in this galaxy is invisible, that the stars you've been admiring are just the luminous tip of a much larger iceberg. The dark matter does not care about your presence. It does not interact with you in any way except through gravity. But it is there, shaping the galaxy's structure, determining its fate, influencing the paths of every star and planet within its embrace. A quirky tidbit: one of the leading candidates for dark matter is a hypothetical particle called a WIMP, or weakly interacting massive particle. WIMPs would be heavy, electrically neutral, and almost completely indifferent to ordinary matter, making them perfect candidates for the invisible mass we observe. But despite decades of searching, no one has ever detected a WIMP directly. Other candidates include axions, primordial black holes, and even more exotic possibilities. The search continues, and the solution may lie in directions no one has yet imagined. Scholars still argue about the properties of dark matter and how it shaped the formation of galaxies like IC1101. In the standard model of cosmology, dark matter clumped together first, forming gravitational wells that ordinary matter later fell into. The visible galaxy we see is built on a foundation of dark matter, like a city built on bedrock. Without dark matter, the structures we observe, galaxies, clusters, the cosmic web, would not exist. Gravity would not have had enough to work with. IC1101's dark matter halo is probably the product of many mergers, just like its stellar population. When galaxies collide and merge, their dark matter halos merge too, combining into larger and larger structures. The halos do not interact with each other except through gravity, passing through each other like two clouds of smoke. Over time, the merged halo settles into a new equilibrium, a larger cocoon of darkness surrounding a larger collection of stars. You think about what it means to live inside such a structure, From your perspective as a human on Earth, the Milky Way's dark matter halo is invisible and undetectable without sophisticated instruments. But it is there, surrounding you right now, a sphere of mysterious particles extending far beyond the visible stars. The same is true for any hypothetical inhabitants of IC 1101. They would live their lives surrounded by dark matter shaped by its gravity, utterly unaware of its presence unless they develop the technology and curiosity to look. There is something poetic about this cosmic architecture. The universe is mostly invisible. Dark matter outweighs ordinary matter 5-1, and dark energy, an even more mysterious component driving the acceleration of cosmic expansion, accounts for nearly 70% of the total energy density. The stars and planets and people that capture our attention are a small minority, a luminous froth on an ocean of darkness. IC 1101, for all its glory, is just the visible face of something much larger and stranger. You drift through the invisible halo, feeling its gravity but seeing nothing. The stars behind you continue to glow, indifferent to the dark matter flowing through them. The universe keeps its secrets close, revealing only what it must, hiding the rest behind a veil of non-interaction. Perhaps someday we will understand what dark matter is. Perhaps someday we will detect it directly. We'll identify the particles responsible. We'll add a new chapter to the physics textbooks. For now, it remains a presence felt but not seen, a foundation sensed but not grasped. Ahead, the journey continues. There is more to explore in IC 1101, more layers to peel back. But for now, simply rest in the knowledge that you are surrounded by mystery, that the visible is always just a fraction of the real, that the universe is far stranger and more wonderful than it appears. You drift through IC 1101, still surrounded by its golden glow and invisible halo, and your mind begins to wander toward a question that has haunted humanity since we first looked up at the stars. Is anyone else out there? In a galaxy containing 100 trillion stars, possibly hundreds of trillions of planets, the odds that at least one world harbours life seem almost overwhelming, and yet we have no evidence, no signals, no signs of anyone waving back across the cosmic void. IC 1101 is vast and ancient and utterly silent. The search for extraterrestrial life is one of the most profound scientific endeavours humans have ever undertaken. It combines astronomy, biology, chemistry, and philosophy into a single question. Are we alone? The answer, if we ever find it, will reshape our understanding of our place in the cosmos. But the search is difficult, perhaps impossibly so, especially when the targets are as remote as IC 1101. A mainstream historical fact: the modern search for extraterrestrial intelligence, or SETI, began in earnest in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for artificial signals. He heard nothing, but the experiment established a template that has been followed ever since. Thousands of stars have been surveyed, billions of radio channels scanned, and still the silence persists. The Fermi paradox, named for physicist Enrico Fermi, who famously asked "Where is everybody?", captures the puzzle. If intelligent life is common, why haven't we detected it? IC 1101 is far too distant for current SETI techniques to probe. The galaxy is over 1 billion light-years away, meaning any signal we detected would have been sent 1 billion years ago. If a civilization in IC 1101 were broadcasting right now, we would not receive the message for another 1 billion years. The distances involved make communication, let alone contact, effectively impossible by any technology we can currently imagine, but the question of habitability is still worth pondering. Astronomers define the habitable zone as the region around a star where temperatures are right for liquid water to exist on a planet's surface. Within IC 1101's 100 trillion stars, there must be countless habitable zones, countless worlds where the chemistry of life might take hold. Some of these worlds would be orbiting stable, long-lived stars, basking in gentle warmth for billions of years. Others would be tidally locked, showing the same face to their sun forever, creating permanent day and night hemispheres. Still others would be moons of gas giants, heated by tidal flexing rather than direct starlight. A quirky tidbit: some astrobiologists speculate that elliptical galaxies like IC 1101 might actually be less hospitable to life than spiral galaxies like the Milky Way. The reasoning is subtle. Ellipticals tend to have older stellar populations and less gas and dust, meaning fewer opportunities for new stars and planets to form. They also experienced intense merger activity in their pasts, which might have sterilized habitable worlds through increased radiation or gravitational disruption. Whether this makes IC 1101 a cosmic desert or merely a different kind of ecosystem remains unknown. Scholars still argue about the factors that influence habitability on galactic scales. Some emphasize the importance of metallicity, the abundance of heavy elements that form the building blocks of rocky planets. Others focus on stellar density, noting that crowded regions might experience more frequent close encounters and disruptions. Still others point to the role of galactic dynamics, suggesting that certain orbits within a galaxy are more stable and hospitable than others. The debate is far from settled, and IC 1101 offers a unique test case for these theories. You float in the golden light, imagining the trillions of potential worlds scattered through this immense galaxy. On some of them, right now, stars are rising and setting. Atmospheres are circulating. Oceans, if they exist, are sloshing against shores. Whether any of those worlds host beings capable of wondering about their place in the universe, we cannot say. The silence is not evidence of absence, but it is humbling nonetheless. And perhaps that is enough for now. The question of life in IC 1101 is unanswerable with current technology, and may remain so for centuries or millennia. But the asking itself is meaningful. It connects us to something larger than our individual lives, larger even than our species. It reminds us that we are part of a cosmos that may or may not include other minds, other stories, other ways of being. Either answer, alone or accompanied, would be profound. You feel a gentle heaviness settling over you, the accumulated weight of distances and numbers and mysteries that cannot be resolved tonight. The stars of IC 1101 continue to burn, indifferent and beautiful. The dark matter halo continues to hold everything in place, and you, small and mortal and wonderfully curious, continue to drift, letting the questions carry you deeper into a soft and welcoming darkness. The gentle warmth of IC 1101's glow remains with you as you drift, but now your perspective begins to shift. You find yourself pulling back slowly, like a camera on an invisible crane, and the galaxy that filled your vision starts to shrink. The amber haze condenses into a distinct shape, an elongated sphere of light against the deeper black of intergalactic space. And as you continue to retreat, you notice that IC 1101 is not alone. Galaxies appear around it, dozens of them, then hundreds, swarming like fireflies in a summer field. Some are small and faint, dwarf galaxies with only a few billion stars each. Others are larger, spirals and ellipticals in their own right, respectable stellar cities by any normal standard. But all of them are dwarfed by IC 1101, which sits at the centre of this cosmic congregation like a monarch surrounded by courtiers. You have entered Able 2029, the galaxy cluster that IC 1101 calls home. Galaxy clusters are the largest gravitationally bound structures in the universe. They form at the intersections of the cosmic web, the filamentary network of dark matter and gas that spans the observable universe like a three-dimensional spider's web. Matter flows along the filaments, pooling at the nodes where multiple filaments meet. Over billions of years, these pools condense into clusters, pulling in galaxies from the surrounding volume and binding them together with gravity. A mainstream historical fact, the study of galaxy clusters began in earnest in the 1950s, when George Abel systematically surveyed the sky for these structures using photographic plates from the Palomar Observatory. His catalogue, published in 1958, identified over 4,000 clusters in the northern sky alone, providing the first comprehensive map of the universe's largest structures. Abel 2029 was one of the clusters he catalogued, a rich concentration of galaxies in the direction of the constellation Virgo. Abel 2029 is classified as a relaxed cluster, meaning it has settled into a relatively stable equilibrium after billions of years of gravitational interactions. The galaxies within it have found their orbits, the hot gas that fills the cluster has distributed itself smoothly, and the whole system has achieved a kind of cosmic balance. At the centre of this balance sits IC1101, the brightest cluster galaxy, or BCG, the dominant member that has grown fat on the accumulated matter of its environment. Brightest cluster galaxies are almost always giant ellipticals, and they share several distinctive properties. They tend to be located at or very near the gravitational centre of their clusters. They tend to be significantly more massive than any other cluster member, and they tend to have extended, diffuse envelopes of stars that blend into the intracluster light, the scattered glow of stars that belong to the cluster as a whole rather than to any individual galaxy. A quirky tidbit: the intracluster light in places like Abel 2029 can contain as many stars as some entire galaxies. These are stars that have been stripped from their parent galaxies during close encounters and mergers, flung out into the space between galaxies but still bound to the cluster as a whole. They form a ghostly haze that fills the cluster, a stellar population without a home, orbiting the collective gravitational centre. When you look at IC1101, you're seeing not just the galaxy itself but also this surrounding haze of liberated stars. You float among the galaxies of Abel 2029, watching them move on their slow, stately orbits. The timescales are almost incomprehensible. A single orbit around the cluster centre might take 1 billion years or more. From a human perspective, the galaxies are frozen in place, unchanging, eternal. But from a cosmic perspective, they are dancing, executing an elaborate gravitational ballet choreographed by dark matter and shaped by billions of years of interactions. Scholars still argue about how clusters like Abel 2029 form and evolve. The standard model of cosmology predicts that clusters grow hierarchically, smaller structures merging to form larger ones over cosmic time. But the details are complex depending on the initial conditions of the universe, the properties of dark matter, the feedback from active galactic nuclei, and a host of other factors. Simulations can reproduce the general features of observed clusters, but matching every detail remains a challenge. IC1101's position at the centre of Abel 2029 is not a coincidence. The largest galaxies and clusters almost always occupy the gravitational centre, because that is where matter naturally accumulates over time. Galaxies that fall into the cluster gradually sink toward the centre through a process called dynamical friction, their motion through the surrounding dark matter acting like a drag that slows them down. The most massive galaxy wins this slow race to the bottom, growing ever larger as it absorbs competitors and accretes in falling material. You think about what this means for IC1101's history. The galaxy did not simply appear at the centre of Abel 2029 fully formed and enormous. It grew there over billions of years, fed by the steady flow of matter from the surrounding cluster. Every galaxy that fell too close became food. Every stream of gas that cooled toward the centre became fuel. IC1101 is not just a galaxy. It is a product of its environment, shaped by the cluster as surely as the cluster is shaped by it. The glow of IC1101 pulses softly at the centre of your vision, surrounded by its retinue of smaller galaxies. The cluster hums with invisible activity, hot gas radiating X-rays, dark matter exerting its silent grip, galaxies falling and merging and being stripped of their stars. But to your eyes, everything seems peaceful, a cosmic city at rest in the night. The violence is too slow to see, the timescales too long to perceive. All you sense is the gentle light of 100 trillion stars, burning at the heart of a structure so vast it defies comprehension. You linger in Abel 2029, floating among its galaxies, and you become aware of something you cannot see with ordinary eyes. The space between galaxies is not empty. It is filled with hot gas, a diffuse plasma that glows in wavelengths far beyond the visible spectrum. This is the intracluster medium, the largest reservoir of ordinary matter in the universe, and it is radiating energy in the form of X-rays. The intracluster medium is shockingly hot, with temperatures reaching tens of millions of degrees. At these temperatures, hydrogen and helium atoms are completely ionized, their electrons stripped away, creating a plasma that interacts with magnetic fields and emits radiation through a process called thermal Bremsstrahlung. X-ray telescopes, orbiting above Earth's atmosphere, can see this radiation, revealing the intracluster medium as a glowing fog that fills the space between galaxies. A mainstream historical fact. The discovery of hot gas in galaxy clusters came in the 1970s, when X-ray telescopes like Uhuru and later the Einstein Observatory detected diffuse X-ray emission from the Coma cluster and others. These observations revolutionized our understanding of clusters, showing that the visible galaxies are just the tip of the iceberg. Most of the ordinary matter in a cluster is not in stars at all. It is in the hot, diffuse gas that fills the space between galaxies. In Abell 2029, the intracluster medium is particularly prominent. X-ray observations reveal a smooth, relaxed distribution of gas, centered on IC 1101 and extending outward for millions of light years. The gas is densest near the cluster center and thins out toward the edges, following the gravitational potential of the dark matter halo. At the very center, where the gravity is strongest, the gas should be cooling, its thermal energy radiating away, causing it to sink and condense. This cooling flow, as it is called, is one of the puzzles of cluster physics. In theory, the hot gas at the center of a relaxed cluster should cool relatively quickly, condensing into cold clouds and forming new stars. But observations show that the cooling rates are much lower than expected, and the central galaxies like IC 1101 are not forming stars at the predicted rates. Something is preventing the gas from cooling, keeping it hot against the natural tendency to radiate and condense. A quirky tidbit. The leading suspect for this heating is the supermassive black hole at the center of IC 1101. Active galactic nuclei, powered by accreting black holes, can inject enormous amounts of energy into their surroundings through jets and outflows. This energy heats the surrounding gas, counteracting the cooling and maintaining a delicate balance. The process is called AGN feedback, and it represents one of the most important discoveries in modern astrophysics. Black holes are not just cosmic vacuum cleaners, they're also cosmic thermostats. You drift through the invisible gas, aware of its presence only through imagination and the knowledge that X-ray telescopes have revealed its glow. The gas is everywhere, suffusing the cluster, pressing against the galaxies from all sides. It is a medium through which galaxies move like ships through water, their passage creating wakes and disturbances that can strip gas from their disks and halos. This stripping process is called Ram pressure stripping, and it is one of the ways that the cluster environment transforms galaxies. A spiral galaxy falling into Abell 2029 would experience the intracluster medium as a fierce wind, blowing against its gas and gradually peeling it away. Over millions of years, the galaxy would lose its ability to form new stars, its spiral arms fading, its color shifting from blue to red. Many of the galaxies in Abell 2029 have already undergone this transformation, their gas stripped away, their star formation quenched, their evolution effectively halted. Scholars still argue about the relative importance of different quenching mechanisms in clusters. Ram pressure stripping is certainly important, but so is gravitational harassment, the cumulative effect of many small gravitational encounters. Strangulation, the removal of a galaxy's gas supply without direct stripping, and mergers. Different mechanisms dominate in different environments and at different times, and untangling their contributions is an ongoing challenge. IC1101 at the centre of the cluster has experienced all of these processes and more. Its enormous size is partly a result of the cluster environment, which has fed it a steady diet of infalling gas and merging galaxies. But the same environment has also shaped its evolution, quenching star formation, heating its gas, transforming it from whatever it once was into the serene giant you see today. IC1101 is a product of its surroundings, inseparable from the cluster that hosts it. You float in the hot, invisible gas, feeling its presence as a kind of cosmic pressure, a gentle warmth that suffuses the cluster from edge to edge. The X-rays it emits are streaming outward even now, some of them destined to be captured by telescopes on or near Earth, converted into images that reveal the hidden structure of the universe. The intra-cluster medium is not empty space. It is a reservoir of matter and energy, a cocoon that cradles galaxies and shapes their fates. And at its heart, IC1101 glows softly, the brightest jewel in a crown made of gas and gravity and light. You have sensed the hot gas filling Abel 2029, and now you turn your attention to something even more dramatic. The jets blasting from EC1101's core. These are structures of pure energy, streams of particles accelerated to nearly the speed of a light by the supermassive black hole at the galaxy's heart. They punch through the surrounding gas like cosmic blowtorches, carving cavities in the intra-cluster medium and shaping the evolution of the entire cluster. The jets of IC1101 are not as famous or as visually striking as those of some other radio galaxies, but they are present and powerful. Radio observations reveal elongated structures extending from the galactic center, regions where relativistic particles spiral through magnetic fields and emit synchrotron radiation. These jets are the visible evidence of the black hole's activity, the exhaust of a cosmic engine that has been running for millions or billions of years. A mainstream historical fact, the discovery that active galactic nuclei could produce jets, dates back to the early days of radio astronomy. In 1918, Heber Curtis observed a curious straight ray extending from the nucleus of the galaxy M87, a feature that was later identified as a relativistic jet powered by a supermassive black hole. Similar jets have since been discovered in thousands of galaxies, ranging from modest outflows to structures spanning millions of light years. The physics of jet formation remains an active area of research, involving the interplay of black holes, accretion disks, and magnetic fields. IC1101's jets interact with the intracluster medium in complex ways. As the relativistic particles stream outward, they push against the surrounding hot gas, inflating bubbles or cavities that appear as voids in X-ray images. These cavities can be enormous, spanning hundreds of thousands of light years, and they contain enormous amounts of energy. The energy in the cavities represents work done by the jets against the surrounding medium, work that heats the gas and prevents it from cooling too rapidly. A quirky tidbit: the cavities inflated by AGN jets are sometimes compared to the bubbles rising in a pot of boiling water, except that these bubbles are filled with relativistic plasma rather than steam, and they rise buoyantly through a medium that is already millions of degrees hot. The analogy breaks down pretty quickly, but it captures the essential physics. Less dense material rises through denser material, carrying energy with it. You watch the jets in your imagination, twin streams of light piercing the amber glow of IC1101 and extending into the surrounding darkness. They are not gentle, they are violent, powerful, capable of disrupting gas clouds and suppressing star formation across scales larger than the entire galaxies. And yet, from your distant perspective, they seem almost delicate, like fountains of light spraying into a cosmic garden. Scholars still argue about how jets are formed and collimated. The basic ingredients are known: a supermassive black hole, a rapidly spinning accretion disk, and strong magnetic fields. But the details of how these ingredients combine to produce a narrow collimated jet remain uncertain. Some models emphasize the role of the black hole's spin, which can extract rotational energy and channel it into the jets. Others focus on the magnetic field geometry, which can confine and accelerate the plasma. Still others invoke instabilities in the accretion disk or the corona of hot gas surrounding it. What is clear is that jets have profound effects on their environments. In IC 1101 and other giant ellipticals, AGN feedback mediated by jets is thought to regulate star formation, keeping the gas hot and preventing it from cooling into the cold clouds that would otherwise collapse into new stars. Without jets, the central galaxies and clusters might be forming stars at rates hundreds of times higher than observed, consuming their gas supplies and transforming into very different kinds of objects. The jets, paradoxically, help keep the galaxies quiescent, maintaining the serene glow that characterizes giant ellipticals. You drift through the jet-carved cavities, sensing the energy they contain, the violence they represent. The cavities are invisible in ordinary light, detectable only through X-ray observations that reveal the absence of hot gas where the bubbles have inflated. They are negative space, defined by what is not there, and yet they contain more energy than billions of stars could release in their entire lifetimes. The universe operates on scales and through mechanisms that defy easy comprehension, and the jets of IC 1101 are just one more example of that cosmic strangeness. Ahead, the journey continues. You have explored EC 1101 stars, its black hole, its dark matter halo, its place within the cluster, the gas that surrounds it, and the jets that shape its environment. But there is more to consider. The galaxy's past and future, the arc of time that stretches from the first moments after the Big Bang to the cold, dark eons yet to come. IC 1101 has a history, and it has a destiny. Both are worth contemplating as you drift deeper into the quiet of the night. You've been drifting through IC 1101 as it exists today, but now your mind turns to time itself. Galaxies are not static objects. They form, evolve, grow, and eventually fade, following trajectories that span billions of years. IC 1101 has already lived for most of the universe's history, and it will continue to exist in some form for eons to come. What did it look like in the past, and what will become of it in the far future? The universe is approximately 13.8 billion years old, and IC 1101 is one of the oldest structures within it. Giant elliptical galaxies at the centres of clusters are thought to have assembled most of their mass relatively early, within the first few billion years after the Big Bang. This means that IC 1101, or something recognisable as its ancestor, was already forming when the universe was young, when the first stars were igniting in the darkness, when the cosmic web was just beginning to take shape. A mainstream historical fact. Our understanding of early galaxy formation comes largely from observations of the distant universe. Because light takes time to travel, looking at remote galaxies is equivalent to looking back in time. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have revealed galaxies as they appeared billions of years ago, showing that the early universe was a chaotic place, filled with small, irregular galaxies undergoing frequent mergers. The giant ellipticals we see today are the descendants of these early structures, the products of billions of years of assembly and evolution. Billions of years ago, IC 1101's ancestor would have looked very different. It might have been a collection of smaller galaxies spiralling around each other, merging and separating and merging again. Star formation would have been more active, with bursts of new stars igniting whenever gas clouds collided and compressed. The supermassive black hole at the centre would have been smaller, still growing through accretion and black hole mergers. The galaxy's colour would have been bluer, reflecting the presence of hot, young stars that have long since died. Over cosmic time, the mergers slowed, the gas was exhausted or expelled, and IC1101 settled into the mature elliptical we see today. The star formation rate dropped to a trickle. The stellar population aged, shifting from blue to yellow to the warm amber glow that now characterizes the galaxy. The black hole continued to grow, eventually reaching its current enormous mass. The galaxy became quiescent, serene, ancient. A quirky tidbit: some astronomers have compared the evolution of giant ellipticals to the life cycle of a fire. In youth, the galaxy burns hot and bright, consuming fuel rapidly, producing dramatic displays of star formation. In maturity, the fire settles into a steady glow, the fuel running low, the flames banking. In old age, the fire becomes embers, still warm but no longer producing new flames. IC1101 is in its ember phase, glowing with the accumulated heat of billions of years of stellar evolution. But what about the future? The universe is still expanding, and that expansion is accelerating, driven by the mysterious influence of dark energy. Over trillions of years, the distances between galaxy clusters will grow, and the cosmic web will stretch and thin. Abell 2029 will become increasingly isolated, its light dimming as the surrounding universe recedes beyond the cosmological horizon. Within the cluster, the galaxies will continue to interact. Mergers will still occur, though less frequently as the cluster runs out of fresh material. IC1101 will continue to grow, absorbing the remaining smaller galaxies and swelling ever larger. Eventually it may consume most of the other galaxies in the cluster, becoming a single, bloated stellar system containing a significant fraction of the cluster's total mass. Scholars still argue about the ultimate fate of such a system. Over truly enormous timescales, tens of trillions of years, the stars will exhaust their fuel and die. White dwarfs will cool into black dwarfs. Neutron stars will spin down and fade. The supermassive black hole will continue to grow, absorbing stars and gas and even other black holes. In the very distant future, the black hole itself will begin to evaporate through Hawking radiation, a process so slow it will take longer than any timescale currently meaningful to contemplate. You float in the amber glow of IC1101, imagining these vast stretches of time. The galaxy that seems so ancient and eternal is, in cosmic terms, still young, still evolving, still on its way to a future that will be unimaginably different from its present. Nothing lasts forever, not even the largest galaxy in the observable universe. But forever is such a long time that the distinction scarcely matters. For now, IC1101 burns, and its burning is beautiful. You have travelled far tonight, across billions of light years and billions of years, exploring a galaxy so vast it makes our home look like a speck of dust. And now, drifting in the soft glow of IC1101, you find yourself thinking about what it means for a species like ours to even know such a thing exists. We are small, we are brief. We live on a single planet orbiting a single star in a single spiral arm of a single galaxy. And yet somehow, we have reached across the cosmos and touched something immense. This is the strange miracle of human consciousness. We did not have to exist. The universe did not have to produce beings capable of wondering about galaxies a billion light years away. The laws of physics could have remained impersonal and unobserved, playing out their consequences in an empty theatre. But here we are, watching, asking, marvelling. The universe has produced at least one set of eyes capable of seeing itself. A mainstream historical fact, the realization that humans occupy a modest position in the cosmic hierarchy, has been called the Copernican Revolution, after the astronomer who proposed that Earth orbits the Sun rather than the reverse. Since Copernicus, each generation of astronomers has pushed our perspective further from the centre. We are not at the centre of the solar system, not at the centre of the Milky Way, not at the centre of the local group, not at the centre of the observable universe. We are by any cosmic measure peripheral, accidental, unimportant, and yet we are the ones doing the measuring. IC1101 does not know you exist. Its 100 trillion stars burn without awareness, following the laws of physics with perfect indifference. The supermassive black hole at its centre consumes matter without curiosity, without intention, without any sense that it is being observed. The galaxy is vast and ancient and utterly unconcerned with the thoughts of a small primate on a small planet in a small corner of a small galaxy. And yet, you know IC1101 exists. You can hold its image in your mind, contemplate its dimensions, wonder about its history and its future. You can ask questions that the galaxy itself cannot ask. Why is it so large? How did it form? What would it be like to live there? Your smallness does not diminish the significance of your knowing. If anything, it amplifies it. Against all odds, a tiny, brief, fragile creature has reached across the void and grasped something of the infinite. A quirky tidbit. Some philosophers and scientists have argued that consciousness is the universe's way of understanding itself. In this view, the evolution of intelligence is not an accident, but a kind of cosmic self-awareness, matter and energy organizing themselves into patterns capable of reflection. IC1101 is not aware of you, but in a sense you are C1101 becoming aware of itself. One small piece of the cosmos looking back at another piece and recognizing a kinship in the shared laws of physics that govern both. You float in the golden light feeling small but not diminished. The vastness of IC1101 is not a threat to your significance. It is an invitation to wonder. The universe is so much larger than you, so much older, so much stranger, and that largeness and oldness and strangeness are themselves gifts, opportunities for awe that would not exist if the cosmos were small and simple and easily comprehended. Scholars still argue about the meaning of cosmic perspective, whether it should inspire humility or pride, despair or wonder. The answer, perhaps, is all of the above. We are humble because we are small. We are proud because we can know we are small. We are despairing because our time is short. We are wondering because shortness and smallness do not prevent us from reaching beyond ourselves. The tension between these feelings is not a problem to be solved. It is a condition to be lived, a feature of consciousness that makes it rich and strange. You let the tension rest inside you, neither pushing it away nor clutching it too tightly. IC1101 glows on, indifferent and beautiful. You glow on too, in your own small way, aware and curious and grateful for the chance to be here, now, drifting through a story about the largest galaxy ever found. You have contemplated the vastness of IC1101, but the galaxy still holds secrets. Despite decades of observation and analysis, there is much we do not know about this cosmic giant. Its exact mass, its precise formation history, the detailed structure of its dark matter halo, all of these remain uncertain, subject to ongoing debate and future discovery. The universe does not give up its mysteries easily, and IC1101 is no exception. One of the biggest uncertainties concerns IC1101's total mass. Estimating the mass of a distant galaxy is difficult, requiring a combination of observations, stellar luminosities, velocity dispersions, gravitational lensing, each with its own sources of error. Different studies have produced different estimates, ranging from tens of trillions of solar masses to over 100 trillion. The uncertainty is not a failure of science. It is a reflection of the genuine difficulty of measuring something so remote and so diffuse. A mainstream historical fact, the techniques for measuring galactic masses have improved dramatically over the past century. Early estimates relied on crude assumptions about the relationship between luminosity and mass. Modern techniques use spectroscopy to measure the velocities of stars and gas, gravitational lensing to infer the bending of light by unseen mass, and computer simulations to model the dynamics of entire systems. Each generation of astronomers refines the estimates of their predecessors, gradually converging on more accurate values. The formation history of IC 1101 is another area of active research. We know that the galaxy grew through mergers and accretion, but the details, when the major mergers occurred, how much mass was added at each stage, how the central black hole grew, remain unclear. Different models make different predictions, and distinguishing between them requires observations that push the limits of current technology. A quirky tidbit: some astronomers have proposed using the properties of IC 1101's globular clusters, the ancient dense star clusters that orbit most large galaxies, to trace its formation history. Globular clusters are thought to form during major star formation events, and their ages, chemical compositions, and orbital properties can provide clues about the mergers and accretion events that built the galaxy. But analysing globular clusters in a galaxy a billion light-years away is extremely challenging, requiring the sharpest possible images and the most sensitive spectrographs. The dark matter halo of IC 1101 is perhaps the greatest mystery of all. We know it exists, because the visible galaxy could not hold together without the additional gravitational pull of invisible mass. But the detailed structure of the halo, its density profile, its shape, its relationship to the baryonic matter, is poorly constrained. Dark matter cannot be observed directly. It can only be inferred from its gravitational effects. And in a system as complex as IC 1101, disentangling those effects from other contributions is a formidable task. Scholars still argue about the nature of dark matter itself. Is it made of WIMPs, axions, primordial black holes, or something else entirely? Different candidates have different properties, and those properties would leave different signatures in the structure of dark matter halos. If we could map the halo of IC 1101 in sufficient detail, we might be able to distinguish between these candidates, providing clues to one of the greatest mysteries in modern physics. But such mapping is beyond current capabilities. The good news is that new telescopes are on the way. The James Webb Space Telescope, already operational, is providing unprecedented infrared views of distant galaxies. The Vera C. Rubin Observatory, scheduled to begin operations soon, will survey the sky with unmatched depth and cadence, discovering new structures and refining our understanding of known ones. The next generation of extremely large telescopes, the 30-meter telescope, the extremely large telescope, the Giant Magellan Telescope, will push the boundaries of what we can observe, resolving details in distant galaxies that are currently blurred beyond recognition. You drift through IC 1101, imagining the observations yet to come. Perhaps, in a few decades, we will have a much clearer picture of this giant, its true mass, its detailed history, the structure of its invisible halo. Perhaps we will discover that it is even larger than we thought, or that it is smaller, or that its properties are stranger than we can currently imagine. The uncertainty is not a weakness. It is an invitation, a promise that the universe still has surprises in store. For now, IC 1101 glows on, keeping its secrets close. But secrets, in science, are temporary. Given enough time and enough curiosity, we will pry them loose. That is what we do. That is what makes us human. You have journeyed far tonight. You have crossed 1 billion light years, explored a galaxy with 100 trillion stars, plunged toward a black hole weighing tens of billions of suns, and floated through the invisible architecture of dark matter and hot gas. You have contemplated timescales that dwarf human history, and asked questions that may never be fully answered. And now, at last, it is time to turn back, to leave IC 1101 behind, to drift slowly toward the rest that awaits you. The galaxy recedes in your vision, shrinking from a vast amber haze to a distant glow, then to a single point of light among billions. Abell 2029 fades with it, the cluster of galaxies becoming just another patch of sky. indistinguishable from the countless other patches that fill the observable universe. You're moving backward now, retracing the journey that brought you here, returning to the familiar coordinates of your small, precious planet, a mainstream historical fact to carry with you. Every element in your body, save hydrogen, was forged in the cores of stars or in the violent explosions that ended their lives. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized in stellar furnaces and scattered into space, eventually coalescing into the cloud of gas and dust that became our solar system. You are, quite literally, made of star stuff. And so is I, C1101. The same processes that built you built the largest galaxy in the observable universe. You are kin, separated only by distance and scale. A quirky tidbit for the road. If you could somehow travel to IC1101 at the speed of light, the journey would take over 1 billion years. By the time you arrived, the sun would have long since swelled into a red giant and shed its outer layers, leaving behind a white dwarf slowly cooling in the darkness. Earth would be gone, its oceans evaporated, its continents melted, its memory preserved only in whatever records might survive elsewhere in the galaxy. The distances involved are not just large, they are prohibitive, barriers that no current technology can overcome. And yet, through light and mathematics and imagination, we have bridged those distances tonight, touching something impossibly remote with the only tools we have. You pass through the local group, recognizing Andromeda as a hazy smudge off to one side, the Milky Way growing ahead of you like a welcoming beacon. The spiral arms become visible, then the central bulge, then the thin disk of stars and dust that is your home. You descend through the galaxy, past globular clusters and nebulae, past other suns with other worlds, past the familiar constellations that have guided travellers for millennia. You are almost home. Scholars will continue to study IC1101, refining measurements, testing theories, asking new questions. The largest galaxy will remain an object of fascination, a benchmark for understanding how galaxies form and evolve. But for you, tonight, the science can rest, the numbers can fade, the equations can wait. You settle back into the embrace of your own world, feeling the soft pull of Earth's gravity, the gentle pressure of the atmosphere, the familiar weight of your own body. The stars are still out there, burning, waiting, keeping their ancient vigils. IC1101 is still out there too, 1 billion light years away, glowing with the light of 100 trillion suns. It will still be there tomorrow and the day after, and for billions of years to come. There is no rush. The universe is patient. You close your eyes, or you let them close, and the images of the journey fade like shadows at dawn. The vast distances become soft. The incomprehensible numbers become quiet. The cosmic scales become gentle. You're small, you're brief, you're here, and that is enough, more than enough. The universe made you, the same way it made IC1101, and both of you are burning in your own ways, adding your light to the darkness. Rest now, the stars will keep. The journey is over, and the quiet has arrived. You lie still, breathing slowly, feeling the soft rhythm of your own heart, the gentle rise and fall of your chest. The universe you explored is still out there, vast and strange and beautiful, but it does not need you to hold it up. It will continue without your attention, the same way it continued for billions of years before you were born. IC1101 fades into a soft memory, a shape made of numbers and light, no longer pressing against your mind. The 100 trillion stars become a gentle glow. The black hole becomes a distant whisper. The dark matter becomes simply darkness, restful and complete. There is nothing more to understand tonight. There is nothing more to carry. Your body is heavy in the best way, sinking into whatever surface supports you, letting gravity do its patient work. Your thoughts are drifting now, untethered from the facts and figures, floating free in the warm space between waking and sleep. The universe hums around you, a low, steady tone that might be the echo of the Big Bang or the sound of your own blood moving through your veins. It does not matter which. Both are music. Let go of the distances. Let go of the scales. Let go of the questions that have no answers tonight. Tomorrow, the cosmos will still be there, waiting for your curiosity to return. But now, there is only rest, only stillness, only the slow fade into a darkness as gentle as the space between stars. Sleep well. The universe will keep your place.